Uh, all right. All right. So yeah, today I'm joined by Jean Rioux, right?
Hmm. Hmm.
And
That's
he's a
right.
professor of philosophy at Benedictine University. Has also served as the chair of the department previously, from my understanding.
Yes. Yeah.
He
Yeah.
did his PhD on Aristotle, Aquinas, and the foundations of arithmetic at the University of St. Thomas. Um, he's published a lot of philosophy papers on many different subjects, but today we're mostly here to talk about his 2023 book, Thomas Aquinas' Mathematical Realism. So, Jean Rowe, thank you for joining me today.
Thank you. Thanks for having me on.
Yeah. Um, so I guess the first question that I would like to ask just to introduce this topic is just, I guess, what is math? You kind of start the book talking about different viewpoints on what exactly is
Hmm.
math. A
Hmm.
lot of mathematicians I know kind of take the Platonic viewpoint, so can you just kind of take us through the viewpoints that you talk about in the book and
Sure.
maybe the essential differences between them?
Sure. So one of the difficulties, and I get to this toward the end of the book and in my conclusion, is that I don't think when people speak about mathematics, they're not always speaking about the same thing. So,
Hmm.
in other words, the word mathematics, historically and especially recently, has taken on a number of different meanings, right? So, people mean different things when they use the word math. So, to say what is math then means you're going to have to say a lot of things, right, to answer that question. So, historically, mathematics was simply the art of calculation, right? So going all the way back to probably the origins of it with the Egyptians or the Greeks in the Western world, right? So something like that. It's just the requirement that people needed to measure things out carefully and precisely, right? So that's mathematics as an art, right? So you're taking quantitative measurements, whether they're continuous or discrete number or lengths or sizes or things like that, and you're manipulating them to come up with a solution that will be of practical use, right? Um, at a certain point, I'm not really an historian of math, but at a certain point, um, people started realizing that you could actually come up with relations, conclusions about different mathematical objects, generally, whether they're in geometry or arithmetic. People started realizing, hey, wait a minute, if you draw a square on the two sides of a right triangle and then you draw a square on the hypotenuse of the right triangle, you can actually demonstrate that those areas are going to be equal to one another. Okay, which that has a certain amount of practicality, for example, you might say. All right, so you could definitely apply it. Say you make sure your foundation on a building is square, or something like that. But it's just something that's marvelous in itself, right? Or even the idea that even better, you might say, is that the diagonal of a square has no common length with any of the sides, which is astonishing, right? And remarkable. So people started realizing that even apart from its practicality, mathematics has what I call a speculative aspect. That's what the medieval philosophers would call it, using the Latin speculative. And for Aristotle and the Greeks, it would be theoria, right? Where we get our word theoretical. So this is knowledge for its own sake. So, okay, right away, we have a split. Mathematics is either a practical skill or art, right, that I use to achieve some goal that's more desirable for me, or it's something that I can study in its own right. Okay. Now, more recently, math has come to include things that don't have any real basis in the world. Okay. So, for instance, anciently, the whole point of what has come to be called the square root of two, for instance, or even worse, I, right? The whole point of it was for the ancients was that that's not a number. Okay. The whole point of it is there's something you cannot do here when I compare the diagonal of a square with its side, right? I can't find a common measure for both of those, which is what they called irrational. Okay, so for them, an irrational number would be a contradiction, right? A number in order to number, it must have a common measure between the sides. So now you have the controversy, right? Is square root of 2 a number, or is it an attempt at numbering? And people will say, well, square root of 2 is dot, 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 dot. And they put an ellipsis at the end. And so as a philosopher, people came along and said, well, wait a minute, I'm not going to let you get away with that. There are no dot, dot, dots in mathematics. Everything in mathematics is precise, right? And measured, right? So to say square root of 2 is a number, that was a controversy. And that raised a question about whether mathematics is real or contains fictional aspects. And more mathematicians who were practical started seeing that the fictional aspects of mathematics still had practical value, right? So there are computations, I'm told, right? I'm not, again, a scientist, but there are computations, I'm told, that can't be made without assuming the square root of -1, which of course is not only not real, it's a contradiction. And yet that contradiction has practical value, okay? So we have in the mathematical realm, we have this transition between practical and speculative, so artistic and speculative, and then even fictional aspects, all right? So if we're going to say what is math, we have to be careful, right, to distinguish what kind of mathematics. If you mean any consideration, whether real or fictional, of relations between quantities, then yeah, that kind of includes everything. Do you see? And that would be, I think that's what people would say math is today. There wouldn't be very many people who would say I is not a number.
I see. See, that's interesting, I guess, to me as a, I remember when I first learned about imaginary numbers, and especially when you do quantum mechanics, they're, they're indisposable.
Yep.
And there was a paper, I think maybe 2022 or 2023 or something like that, talking about how imaginary numbers or something with an imaginary form, which whenever you square it, it goes to -1.
Right.
Whether or not that's exactly the square root of -1 or it's some sort of geometrical operator that, you act on it twice and then you get -1. It seems to be necessary. But
so you're saying the square root, you're saying I squared is equal to -1, right? So you can actually perform an operation on it and get something rational from it.
I see. Okay, but you wouldn't. Okay, so would you say then that the square root of -1, would you say that that's only a practical application, or would you say that it's not real? Because it seems to be. I mean, so I understand from the Aristotelian kind of position, you sort of abstract from experience, and I'd like to talk a little bit, I guess, exactly what that means later. But
Sure.
it seems that you can get through like higher levels of experience, higher levels of abstraction. You can start with adding. Oh, I can add 1 + 1 apple and I get 2 apples, or 1 + 1 box and I get 2 boxes, where you can do a higher level abstraction where you say like I have A + B and it'll equal C, and it has some sort of formula.
Right.
So is there a way that you distinguish that in a way, like higher
Oh
levels of
yeah.
experience?
So So what you're talking about then is the extension of number classes, right? So for instance, start with just the whole numbers, and you say, okay, what are the whole numbers? Well, those that what we call the counting numbers for our purposes here. So you say, yeah, if I have objects there, I can count 1, 2, 3, 4, 5, 6, 7, and so on. Okay. Now there are operations we perform on the whole numbers, and we say, okay, if I add 2 numbers, I'm going to get a number. But then I go to subtraction and I say, wait a minute, if I subtract 2 numbers, I don't necessarily get a number, right? So if I subtract the greater from the smaller, in the real world, you'd say, well, you can't. Okay. But if you actually allow the operation of subtraction to extend over the whole range of the number class you're starting with, and you insist that subtraction always yields a number, you've created a new number class, namely the negatives. Do you see?
Yeah.
All right. And so right now, then you've sort of built a new class of number. All right. And the same holds true for square root of 2, for instance. Right. It's taking squaring, right, and applying it to a number and assuming that when you take the square root of a number and applying it to a number, you're going to get a number,
I
right?
see.
And of course, what you get is what I'd say, well, there's a question as to whether or not that's really a number. So
Hmm.
we speak of operations, mathematical operations that are closed and open.
Right, right.
Right? So earlier, long ago, they would have said, well, subtraction is closed to the integers. What does that mean? Well, I'm sorry, subtraction is closed to the wholes. That means if you subtract a whole number from a whole number, you don't necessarily get a whole number.
Right.
Okay? Once you open it up, then you say, well, it may be closed to the whole numbers, but it's open to the integers
Mm.
because the integers include both positive and negative numbers. Do you see?
Right, yeah.
So square root of -1, then, you're just saying, I'm going to open up square root, not just to things that would reasonably have a square root,
Yeah.
but even to negatives.
Hmm.
And I'm
Okay.
going to define the result as a number. And I'll call it an imaginary number.
Interesting. Okay. So you
Yeah.
wouldn't you
Yeah.
might not even you would even say that maybe like the irrational numbers or the negative numbers aren't real, I guess, in the sense that you're
Right.
talking about.
They're real in the sense of real numbers, like the real
Yeah.
number class. Okay.
Yeah.
But they're not real in the sense of having uh, correlates outside the mind.
I see.
Yeah.
Okay. I think it would be helpful here then to maybe talk about the difference in Platonic and Aristotelian conception
Okay.
of
Sure.
mathematics.
Sure.
Um, which I asked my audience a little just put out a quick post. I was like, hey, I'm talking to this guy, Gene
Okay.
Rowe, that wrote this book. If
Yep.
you have any questions, let me know.
Oh,
And some
wonderful.
people were interested. This is one of the main things that I was trying to answer when
Okay.
I was reading books like yours. Trying to figure out because I understand that, in the Platonic view, it's pretty easy to understand math. I mean, he kind of has like a primacy to math where it's like you have these mathematical objects and they're kind of the most real, like eternal forms, and then these other things exist. And
Mm-hmm.
I saw some people saying that they were interested because of course math has this kind of like eternality to it, and it doesn't
Yep.
really seem to exist in the real world, at least in the same way,
Right.
like,
Sure. Sure.
you don't usually see perfect spheres in the world. So
Usually,
usually, and I'd really
I
love
don't
to get
think
to
you
that.
ever see spheres in the world.
Okay, great. Okay,
Okay.
we're definitely gonna talk about that for
All
sure.
right.
But
Good.
if you could talk about like how, as an Aristotelian Thomistic thinker, you could say, oh, maybe these things have a primacy in the real world, but nonetheless, you can kind of see their perfection in like this Platonic sense. Could you maybe
Sure.
talk about
Sure.
the
Sure. Sure.
difference?
Okay. So you remember I made the distinction between the art and of mathematics and and pure mathematics. Aristotle would call that an episteme, or what in the medieval period it would be called a science.
Hmm.
Not a science like physics, right?
Right.
But a science like taking principles and demonstrating conclusions that follow necessarily. Okay. So both Aristotle and Aquinas will claim that that whole process begins with abstraction. Okay. And abstraction begins with reality. So you have what's come to be called, and they were fully aware of this, the precision problem in mathematics.
Could you
Okay.
just really quickly explain what abstraction is?
Yeah, I was
Okay.
going to fill it out a little bit, but
Okay.
abstraction is separating in thought things which coexist in reality.
Okay.
So there are two forms for Aristotelians and Thomists. One is understanding what, say, a number of different things have in common. Okay, so that's called abstraction of the whole. So, for instance, I see a pine tree, a pine tree, a pine tree, and a pine tree, but my thought of a pine tree is not identical with any of those four, right? So even if they were all destroyed, I still understand what a pine tree is, okay? So somehow what's out there has made it into my mind and left behind the individual differentiating characteristics, okay? That's called abstraction. So that's why we say something is abstract, is we say it's not concrete. It's not an individual, it's a concept or a thought. Now, Plato would say the reason why there can be four pines, as you said, right, is that there's pineness up there. Everyone always gestures up. right, when it comes to Plato. And it's an immaterial form that all these four participate in. So the difference between Aristotle and Plato is that Aristotle said universals are present in the mind. And Plato said universals are real and outside the mind. Okay? So that's one form of abstraction. And of course, that has to happen in mathematics too. Right? So when I say 2 + 2 is equal to 4, there are two twos there.
Right.
Right.
Because you're
So,
talking about two different subjects necessarily.
yeah, if it's
Yeah.
really the same two, then I'm not adding.
Right.
I'm just saying 2 is 2, and it's not 4. Okay.
Hmm.
So that abstraction of the whole is something that presupposes multiple individuals, and then you get a common nature out of it. Math does that too. But there's a very special kind of abstraction that math does in addition to that, and it's called formal abstraction. Okay. So what a mathematician does is looks at an external object and ignores certain aspects about it that individuate it. Okay. So for purposes of the discussion, I'm looking at a sphere. Okay. And the natural philosopher, say an astronomer, might say, oh, that's the moon. And that's important for the natural philosopher to say, it's the moon, its composition is this, its movement is this, its size is this, it's, and so on. I mean, whatever it's made up of. But the mathematician doesn't care about any of that. Okay. All he's interested in is in the shape,
Right.
because the shape is a spherical shape. So we say math is abstract in both ways. It's understanding, say, spheres in general, not some particular one. And it's only focusing upon their quantitative aspects, for instance, shape or number. Okay. So that's what we mean by abstraction, is looking at things, understanding them independently of either individuating characteristics or all the characteristics, but the one I'm focused on, which is quantity for math.
Right.
Okay. So, and this is the point, abstraction presupposes reality.
Mm. Right.
Okay.
I
So you can't
see.
abstract without something to abstract from.
I see. Okay. Um, Interesting.
Okay.
Um,
Okay. That was kind of a sidebar. There wasn't.
okay.
You were
Okay.
asking me
No, keep
about
going.
abstraction.
Yeah.
And then we were going to the question of, what about the precision problem?
Hmm.
Okay. So there are no spheres. In fact, there are no straight lines. Nothing has any regular curvature in the world.
Hmm.
Right. If you drill down far enough, anything that looks straight, you'll find is not.
Right.
Okay. And it's not even regularly curved. Okay. So matter itself doesn't seem to fit at all with geometry.
Hmm.
Okay. And I think, and Aquinas and Aristotle are both aware of this, right? They'll say, listen, it sounds like the line the mathematician considers, the geometer considers, is not the physical line.
Right.
So how can we say we're abstracting? Okay. So here's what I think is happening. If you look, for instance, at geometry, arithmetic is an easier case even, but you look at geometry and you look at something like Euclid's Elements, which for them, I mean, Euclid came after Aristotle, but for them, that would be the paradigm of a science in that sense, right? You
Right.
start with definitions, you have universal principles, then you demonstrate conclusions. And you say, well, where do they get their straight line? You're not going to do geometry without a straight line. And I think it's this. You don't get straight lines from straight lines in the world. Okay? You don't get circles from circles in the world. What you do have in the world that's precise is dimension.
Okay.
All right. So we know things have length and breadth and depth. Okay. So if things have 3 dimensions, they necessarily have 2 dimensions. And if things have 2 dimensions, they necessarily have 1 dimension. Unidimensionality is the straight line.
I see. Hmm.
So we get our notion of straight line not from any particular object's shape. We get our notion of straight line from knowing that 3 implies 2 implies 1. And unidimensionality is necessarily straight.
Right.
That's
Okay.
what straightness is.
Right.
Okay. So now we have a straight line. What are we going to do with it?
I
Well,
see.
we're going to fix one point and spin it around itself.
Mm,
We do that in our imagination.
right.
Then we get a circle. And with
Mm,
a straight line in a circle, you can do anything.
fascinating. Okay.
So geometry then is constructed, but on the basis of realities, namely dimensionality, the unidimensionality. By the way, we can get planes too, and regular solids, right? And things like that. And
Right.
you use those principles to then manufacture things like triangles, okay, squares, pentagons.
Interesting. Okay. So
Yeah.
I think you've done a really fantastic job of talking of how we get from reality to these abstract objects
Okay, good.
through things like abstraction.
Okay.
I know that Aristotle and Aquinas would talk about things having sort of like potential forms, right? That you sort of actualize in your intellect. You can see that
Yes.
something's
Yes.
kind of
Yes. Yes.
approximating a sphere, and
Yes.
you can
Yes.
like,
Yes.
I can see what it's approximating.
Yes.
Or you kind
Yes.
of take things away to their simplest forms to where you get things like unidimensionality and right, you
Okay.
can move it in a circle and stuff like that.
Yeah.
I
Yeah.
would really love to hear your opinion, I guess, more on the precision problem
Right.
of how much our abstractions can really apply to the natural world then at that level.
Sure. Okay.
Because,
So,
if
mhm,
nothing really is a circle, if no, if
right.
we don't see perfect circles, it happened in a process that you very reasonably explained. Then why is it whenever we call something circle, it's not insane? It's not totally wrong, or it's
Well,
kind
I
of
think our language is approximate.
right.
Okay, so I think if you put it to them, no one is going to say anything in the physical world is a perfect straight line or a perfect circle. The fact that we actually use the phrase perfect circle
Hmm.
indicates that it should be redundant.
Hmm.
A perfect circle is not a circle at all. I mean, an imperfect circle is not a circle at all.
Hmm.
Does that make sense?
Right, yeah.
Okay, so and
But you
similarly,
could still say it has the form of a circle in a way. Like you could say something has an accidental form of circularity, and that wouldn't necessarily be completely wrong. I don't think you're more of an expert than I am, but
well, it's not a question of expertise. Think of your language, right? Is any diminishment from the regular curvature of a circle enough to say it's no longer a circle?
I mean, I guess I wouldn't say it's not a perfect circle for sure.
Well, again, so I think here we're just doing semantics, right?
Yeah, okay.
For me, I define a circle as a plane figure, all the points of which are equidistant from the center.
Hmm.
Okay.
Yeah, okay. I mean, well then, yeah, if it breaks with that definition, you could say it's by definition not a circle.
Okay. So
Yeah.
if you're saying then there's a perfect circle and an imperfect circle, tell me what a circle is.
I mean, I guess I couldn't really define it other than the perfect circle, but I mean,
But then an imperfect circle would not be a circle.
right, yeah. Hmm.
So either the words perfect and imperfect are redundant, or we're just approximating. And there's a standard, and
Hmm.
then there's something that is a diminishment from it. So, for instance, you would say, if I have a math problem that requires a sum, and I say, I came up with 1,233, and the correct answer is 1,234, and someone else said I got two.
Yeah, right.
We could distinguish between something that's almost there
Right,
and
yeah.
something that's way off, right?
Right, right.
So I think again, we're just talking practical, right?
Hmm.
We have to work with the physical world.
Right,
We have, I think, a demonstration about the nature of circles in our mind.
right.
And we can also recognize that nothing in the world actually matches that.
Mm.
Okay. But we can only do that. We can only say that's not quite a circle if we have a circle.
Yeah, you can see that there's something that it lacks. Like there's a standard by which
Right.
you're measuring it. Yeah.
Right.
So
Right.
I also wonder because there's another book and I'm blanking on the author's name, but it's something about Aristotle's mathematical realism. It was released before your book, but
Okay.
kind of the same.
Franklin, maybe? Was it Franklin?
Could have been Franklin. I don't know.
Mm-hmm.
Uh,
Okay.
yeah, I have the book. I have the book somewhere, but I'm not going to go look for it. But
No, that's okay.
they he talks about the fact of this problem of idealization
Yeah.
um, in applied mathematics, and he's saying that you know one of the reasons Aristotle thought of this as such a problem that's like irresolvable is because the mathematics wasn't advanced enough in a way.
Mm,
And
mm.
so there is a sense in which, okay, something might not be a circle, but maybe what I could do, say I'm trying to model the surface area of the Earth.
Yep.
Okay, it's obviously has a component of a sphere on it. So I could say
It's
that
not spherical, but yeah, go
it's
ahead.
not spherical, but you could see that it approximates
Sure,
sphericity.
of course.
And so maybe I'm trying to model the surface area of a sphere. I would maybe, sorry, model the surface area of the Earth. I would maybe say it's the surface area of the sphere of the average radius of the Earth
Hmm.
plus these perturbations.
Hmm.
And maybe they're like these little like triangles that I draw, on the
Sure,
Earth, to
sure,
represent mountains and valleys. And then I'll get
sure.
closer. And then maybe I'll
Closer.
draw triangles on those triangles. And then
Yeah.
maybe I'll do
Well, you're just doing calculus. I mean, that's what you're doing, which
right.
is which is the science of approximation.
Okay. Yeah, so I mean,
I mean,
it
you're
is a
just saying the limit of this process would be this,
mhm,
right? So it's like trying to express the area of a circle using triangles or squares. We know you can't do it, right?
mhm,
But we know the process has a limit. You can't go outside the circle, right? It can approximate closer and closer to the inside of the circle.
mhm.
So then we say, well, the limit of that process is the area of a circle, pi r squared, right? So,
You're
but
right.
now, of course, pi is what?
It's an infinite, right? Yeah, you
Yeah,
can't
and so
really.
and so that's always going to be an approximation in
Mm,
practical terms. So I don't see how the precision problem. See, there's the precision problem is the problem of going in.
okay.
You're talking about practically applying an ideal to the world.
Yes.
That's going out. But
Okay.
but really, for my purposes, the going in problem has been solved
Okay.
because there aren't approximate straight lines in the world.
Right. Yeah,
Because there is unidimensionality, at least, there's real straightness out there.
I see.
Okay. Then from there, it's a question of using our imagination to construct things on the basis of straight lines and then, of course, circles and all of that.
Yeah. Yeah. I do think, yeah, the process that you said is going in. I totally agree with that. But then I
Okay.
guess I'm kind of stuck with this, the unreasonable effectiveness of mathematics and the natural sciences, where it's like, uh, sometimes it seems like to go back kind of to the Earth example, um, because it's not a sphere, but I can always add things that get me closer. And I might be
Yep.
adding infinite things, and it might come down to
Wait,
scanning.
you might, or you will.
I guess it would be complicated because,
We're talking about straight lines, right? We're talking about plane figures.
mhm. But I guess I'm thinking of composite geometric objects as well.
I know. Yeah.
Okay.
So
Yeah.
we're talking about curvatures, for instance,
Yeah, sure.
or
Right.
straight figures, or plane figures.
Hmm.
It's interesting if you look at modern technology, right,
Hmm.
and the generation of three-dimensional objects on a two-dimensional plane
Hmm.
using software,
Right.
right? So what they do
Hmm.
is they divide curved planes up
Hmm.
into as many polygons as triangles as it takes, where you won't see the difference.
Right.
Okay, so even the screen we're both looking at is composed of discrete units.
Right.
So when you talk about geometry, like I'm talking about it, none of that is relevant.
Mm.
Okay, when you talk about actually applying, say, I want to compute the value of the surface of a perturbated sphere,
Hmm.
I'm going to say, well, you're gonna come close. You may
Yeah.
come very, very close, but you'll never get there, right?
Right.
Okay, because we really cannot square the circle, or we really cannot, one might say, polygonize the sphere. A sphere is not just an infinitely sided square, right?
Right. Right.
Or polyhedron.
Right. No,
Mm-hmm.
this is very interesting. And I think the other thing as well, I guess the thing that I thought of, because I was kind of as a physicist, I usually don't think of it in terms as this, but a lot of my colleagues will think of the of nature kind of as math. It's kind of like
Just math.
manifestation.
Yeah,
Yeah,
sure.
manifestations of math. I mean, that's
Yep,
kind of what we
yep,
do
yep,
methodologically. I think
yep,
the idea of
yep.
physics as a mathematical science is a much better descriptor than, I guess, physics, because it kind of, if you say physics, it kind of makes it sound like we're doing a science in the Aristotelian sense. Aristotle would say like, if you're studying the Earth as a sphere, you're not studying the Earth, you're studying a sphere that is like attached to the Earth in a way. You're studying the Earth qua sphere, right? Which is
Right,
what
right.
we're more doing as physicists rather than actually studying the Earth. And there's a separation. But I think it's a good science, like there's things that we can learn from this. But I think the methodology usually will lead people to a certain ontology where it's like, okay, well,
Yep, yep,
nature
yep,
just is math.
yep. Is
Um,
numbers, yeah. Eddington said that.
yeah, right.
So he basically said it's just numbers. Everything is just numbers. He's a
Yeah,
Pythagorean, by the way.
r right. And
Okay,
so, whenever you kind of have that worldview of everything, yeah, sorry, I was trying to kind of argue against this worldview of everything being
okay,
math. And the thing that
okay,
I kind of saw as a rebuttal to my idea is some of the precision that we get to do things with using
okay,
mathematical objects.
okay.
But I guess one of the things that I thought of is usually if we want to get precision with real world objects these days, you
Yeah,
have to end up
yeah.
using simulations. I think that that's the main way to do it. If you want to model, say, the drag on a F1 car, you have to
Hmm.
use finite element analysis where you like have a scan of the
You mean
car.
is there an infinite element analysis?
No, there's not infinite.
I'd like to see it if there is one. Otherwise, the word finite element analysis is finite. I
Right,
mean,
exactly.
okay,
But
okay,
no, I agree. I'm agreeing with you. But
yep,
you put this scan of the car, but you put it onto a computer, and then
yep,
you run this finite element
yep,
analysis in, and
yep.
that can be incredibly precise. But I think the
Okay.
thing that I realized that kind of changed my mind on this not necessarily being a success of math is by scanning something in, you're putting in a new sensible object. You're giving it its own matter in the form of the computer
Mm,
and then it kind of
mm.
has its own sensibility and you use the structural relations that you know between,
I really have no difficulty in physical things following mathematical laws.
Oh yeah, no, I
Okay,
guess I don't do that either, but I was just saying, just to your point of analysis always being finite, it's like even in the sense
sure.
of computers where you can get it incredibly precise, you are
Okay, so when you
um,
say incredibly precise, okay, do you
not infinitely
distinguish?
precise.
Okay, do you
Yeah.
distinguish between precise and accurate?
Oh, for sure. Yeah.
So accurate to a degree of precision is what we say.
Yeah.
Okay, infinitely precise would be accurate.
I mean,
There is a way things are, right?
yes.
So if I'm counting apples or I'm counting the 12 apostles, 12 is infinitely precise.
Yeah.
Okay,
That was
because
that
it's
was another thing I wanted to pick your brain on
okay. Go
is
ahead.
the
Go
precision
ahead.
of
Go
I
ahead.
guess whole numbers versus geometrical objects because the geometric
Okay.
objects kind of exist in a continuum and you have discrete numbers exist um,
Right.
on points. So I guess yeah, I
On
was interested
point.
to hear your or they're discretized.
Okay. Okay. Do you think numbers have existence in reality?
Yeah, I do. Yeah.
So you really have two eyes.
Yes.
So not only are eyes there, two's there too.
I mean, I have two is there. I mean, it is the quantity of my eyes.
Yeah, but if there were no rational beings in the world, dogs would still have two eyes.
Right.
They'd have eyes, and there'd be two of them. You can't just have I-ness in a dog; it has to be two-ness too.
Sure.
Okay, so you say, all right, what about the precision problem there? All right,
Yeah.
if arithmetic begins in abstraction two, then where have you ever seen, this is Descartes, right? Where have you ever seen something that is distinct and you can take it all in with a trillion parts? Okay. No. It's impossible for the human person to abstract the number trillion from the world.
Right. Okay. Yes.
Say, where do we get it? Okay.
Yeah.
Well, what we do abstract from the world is one.
Right.
There are real ones out there.
Hmm.
Any number, like I'm taking the line and spinning it around, making a circle, or taking lines and making a triangle, constructing in my mind, I can construct any number.
Right. I
Okay.
see. So it's the same
So
thing as unidimensionality, kind of.
exactly, you're
Yeah.
abstracting the fundamental principle of geometry or the
Hmm.
fundamental principle of arithmetic.
Hmm.
And from that point on, it's the constructive imagination making these objects that we contemplate.
Right.
So we know that a million is a square, right? But I've never abstracted a million from what I mean. It's a square number. I've never abstracted a million from the physical world. I never encountered it. In
Hmm.
fact, so that's what Descartes says. He says everyone understands. He uses the term chiliagon, which is a thousand-sided figure. He
Yeah.
says, but no one can imagine
Yeah. Right.
or sense it.
Right.
So I think the precision problem for geometry is more difficult because imprecision leads to a difference in the kind of thing you're looking at. Still, in arithmetic, the idea that we don't abstract all the objects, all the numbers from the external world, first of all, you can't because it would be an infinite process. But secondly, we don't encounter things with that number of parts in the physical world. So all of that's constructed. Okay. So why would Aristotle and Aquinas reject negative numbers? Okay. There's a good reason why, for example, I don't think non-Euclidean geometry is a science, right? Or non-Euclidean geometries are sciences, like Euclid is.
Okay.
Right? I don't think extensions to the whole numbers can be studied as realities in the same way as the whole numbers can. Okay, because I don't think those things are compatible with those principles that you took in from the world.
I see. I mean, you could imagine, if you have a quantity one that you've abstracted from nature and
Yep,
you can kind of multiply it in a way. You can kind of
sure.
conceive of multiplying that in one way. I
Mm-hmm.
mean, you can also, I guess, conceive of multiplying it in a different direction. No, or
What does it mean to multiply it? You're talking about adding, right? Because multiplication is just addition.
sure. Yeah. Okay. Yeah.
Okay. What other direction is there for adding except bigger?
I see. Okay.
Yeah. Yeah.
And so, okay. And again, you would just say that it's more of a useful tool. I mean, you could say,
Yeah, sure.
what about in the sense of direction? You could say that, I have a pen and I stack another pen on top of this pen.
Yeah.
So I have
Yeah.
two pens long
Yes. Yes.
structure, or I could do it in another direction.
Yeah.
Do you think maybe that way you could abstract a negative number in a way where you could say like, oh, I
To the
stack.
left of zero,
Yeah, I guess so.
because when we do math, we abstract from things like left and right and direction.
Oh, okay.
We're only concerned with quantity,
I see.
with how much.
Right.
So it's a nice analogy to say, well, to the left of zero is -1.
Right.
But frankly, when I look at a number line, let's say from 0 to 10 and from 0 to -10, I'm just saying, oh, here's a line with 20 parts.
I see. Right.
There's no
And then
negative here
and
at
then
all.
I guess like the 0 point that you define is more of like a convenience. It's kind of a
It's
technique.
just it's just the midpoint of the
I see.
line.
Right.
And of course, for them, zero would not be a number either.
I was going to ask about that. Yeah.
Yes, yeah, zero cannot be a number. So I once had a colleague here at Benedictine, and one year he was a mathematician, and
Hmm.
one year, long, long ago, we received the terrible news that we wouldn't be getting a raise that year. And so I went to our mathematician and I said, at least we're getting a raise. And he said, no, we're not. And I said, yes, according to you, we are, because we're getting a 0% raise. And he said, 0% is not a raise. And I had him, right? Because then zero is not a number. Okay.
Well, I mean, it could be a number that doesn't raise.
A number that doesn't raise. It's not a, if you say, uh, I have a number of dollars that I got this year over and above my last year's salary, people would expect you to pull something out of your pocket. But
Interesting.
zero is not a number of dollars.
Hmm.
So
Would you
I
say
think,
that maybe zero could represent a potentiality for a number in a way? It's like a placeholder where you could potentially put a number, or I guess
put
how
a
would you describe
number, I
zero?
don't, I mean, again, numbers are only how many's.
Okay.
There's nothing beyond number. Now, if you're gonna, again, I mean, what you're doing is exactly right. I mean, that's exactly what we've done. We've brought position into arithmetic, and then negative numbers make sense, right? We've brought red ink into accounting, and negative numbers make sense, but it's really just blue ink or red ink. They're both colors of ink, right? But the red is not a negative anything. It's a positive red, right? But what we do is we say, well, it's red because the number subtracted from is smaller than the number I'm subtracting, right? But then I would
Right.
say, well, you're just three in a hole, right?
Okay. Yeah.
Okay.
And so this seems to me more like you're not necessarily, are you just denying that they're numbers, or are you denying that they have any reality in that
Well,
sense?
okay. Number, define number.
From your definition, I would guess, a quantity of something.
Yeah.
Yeah.
How much is,
Yeah.
or
Yeah.
how many really
Hmm.
is a number. Now, of course, that's what I say in the last chapter. People don't always use words with the same meaning.
Right.
Right? So part of our discussion, I'm sure, okay, has to do with, well, wait a minute. We call it a number line. And to the left of zero, those are negative. We use the word number to describe that. And I'm perfectly granting that. What I'm not granting is that you haven't changed the definition of number when you
Right.
do that. Okay.
Okay.
Yeah.
Yeah, but then you could maybe say that things have a quantity and maybe they have a direction in a way. Like I think numbers kind of happen pretty naturally if you think about a vector, something that has a quantity in the sense of its length, right?
Yeah.
But it maybe points in a certain direction. And I think
Yeah.
from there where you kind of distinguish the quantity, what you would say is then for you, you'd say is the number. But then you distinguish,
It's just whatever direction it's pointing. Okay, let me
yeah.
let me emphasize then.
Mhm.
So, is the negative number compatible with what you abstracted from reality?
I think it is. I think it is compatible. I mean, like you can see it, I guess, in your experience, like abstracting from reality, just in the idea of directions. I mean, like if the only
No,
thing
no,
that
no. I'm
I,
saying so. So when we started arithmetic, remember we abstracted the unit.
right,
We say there are units in the world,
yes,
right? So the very idea of a unit is, I mean, it's one.
yeah, yeah,
If you divide it, what you get are two, not half.
hmm,
Okay, so if one, the thing you abstract from the world, is unit, and number is a how many of units, negative number is not compatible with that unit.
yeah. But I guess what I mean, is we still have this unit, right? But we could imagine, a unit. Yeah, I mean, so this pen has a unit, right? I mean, it's
Is a
one
unit.
pen, right?
Sure,
And
sure.
so I could talk about things pointing in certain directions. And
Yeah.
then I could say, okay, well, I have this direction opposite of this direction. And maybe
Okay.
I'm not, this is not, there's not a different number anymore. I agree with you that we have
Okay.
the quantity one, right? But you
Yeah.
could say, in order to denote something pointing in the opposite direction, maybe that's how we abstract
Right.
negative, just this negates this. These are opposite
But
directions.
there's
If I move,
nothing. There's nothing being. See, a negation is a taking away of something. Right.
yeah, so it wouldn't be a number. I think
Oh,
that
okay. Okay.
I'm
Okay.
trying to say, yeah. So just
Okay.
building on
So
your system. So it's not a number, but it is something that maybe we can do logic with in the form of mathematics.
well, why'd you introduce that term? That is in the form of mathematics. I fully grant that there's a science of direction.
Yeah. Okay.
Okay, but it's called physics.
Okay.
It's not
So
called math.
yeah, yeah.
Or if you call it math, it's not this. I'm speaking or looking at the real world. Right? Direction is a physical property. Right? There's no left and right. in the world unless you're talking about things that have faces, right? Direction is, where, how shall I say it? After Einstein, right? What is direction?
I mean, yeah, it's
Only
typically,
time, maybe time
yeah,
is an absolute direction, but
it's typically hard to define a specific direction, right?
okay. So is a direction real? Is what I'm asking.
I mean, I think that you can definitely define directions, and then you can talk about the same ideas of directions. You can even have a variation in quantity, though, in Einstein's general relativity, which, at that point, I mean, you can still say you see something like a different perspective of quantity possibly, but you could still
Right.
talk about like quantities, like, oh, I saw two, oh, I saw one. You would know what you're talking about in the same way that maybe if you could figure out something that you and other people agreed upon, directions, then you could talk about directions from there. I would agree that maybe
Is
there's
there
no,
no absolute direction, right? Though.
no, there isn't, no, I mean, like
Okay.
not universal, right? But you can always agree, like we can agree on north, south, east, west, I guess, in the perspective of Earth. Even though east and west is a little bit dubious, right? But you can
Well,
talk about north and south.
north is just along a curve. I mean, I don't get that. More
I
anything
guess, yeah, but
more.
you could still do it locally, I guess. Like I could say, like I live northeast of you.
Okay, but my question is, I mean, so I'm saying math is concerned with reality,
Hmm.
with the way things are,
Hmm.
right? And you can't escape again unidimensionality of space. That's real. You
Hmm.
can't dispense with the reality of unity that some things have. Okay, but when I get to something like direction, and I can't even decide whether it's real. Do you get what I'm saying? North, south, east, and west aren't real.
I mean, I guess they're not absolute.
Okay,
They can in fact change, but
so if they're not, you're saying
they're
if
not
they're
universal.
relative, they're real. They're still real.
Yeah,
So I really have a speed when someone passes by me. I both am at rest and am moving.
I mean, you would have, yeah, I mean, you would have different, I guess, from that perspective, you would have different reference frames, but you and another person could agree on a reference frame and then make measurements from there. And then you could say
Oh
that,
yeah. Oh yeah. Don't get me wrong. So let me really put a fine point on it.
okay,
So someone goes by me with the only two objects in the universe.
yeah,
Am I at rest or am I moving? What's real? Can I be both?
yeah. I mean, it's hard to define, right? I mean, you'll say something different than what the other person will say typically.
Yes, but is there a fact of the matter?
I mean, there's not an absolute fact of the matter.
Okay. So
Yeah.
that's what I would call reality.
Okay. So
Is
only,
something that is the way it is independently of perspective. So even if all rational beings were to cease to exist, right, there must be a fact of the matter here. Otherwise, everything would be relative to the human mind. And so we're not even talking about objective truth at all. Right? It all would be subjective. No? Yes?
I mean, no, I see what you're saying. I see what your
Okay.
concern is. But I would say that even some things like number can vary.
Take a fraction. Okay. So what we abstract from the world is a unit. Like you said, one pen. So strictly speaking, half is not a number because it contradicts the very nature of the unit, which is not to be divided.
But I guess you could still say it's real, right? It's just not a number, maybe from your definition.
Half?
Hmm.
Yeah, it might be relation, perhaps. I'm not sure. You mean physically cut something?
Um, I mean, I could just say, yeah, I mean, I could just say that's real. I mean, in any sense, sure, to physically cut something. I mean, in
Okay,
a half.
because if you say there's a half in the whole pen, there's also a quarter in the whole pen,
Right. And then you end
and
up with the
so there'd be an
precision
infinite
problems.
number of
Yeah,
things
right.
in one little pen.
Yeah. I mean,
So
but I could also say something that's very easily, broken up in a way. I don't know. I could say that I have a jar that has two marbles and then I have the marbles, right?
actually, there's still two. You mean, or are you talking about cutting them each marble in half
I mean, I guess just take a marble out. I have half the marbles that I had before.
in the jar?
Yeah.
You could say that, but really what you have is two divided by one. You have one marble over here and one marble over here. You can't,
Okay.
I mean, unless you physically divide them, if you have a discrete number of different things right in front of you, you don't change their number just by moving them around. Again, place is something we're going to abstract from.
Okay. Interesting.
So I don't think, let me put it this way, I don't think by moving one marble, somehow you've changed anything about quantity in the entire universe. There still are two.
Yeah,
All you've done is you've changed their place, which
I
is
see.
a physical question, not a mathematical question.
Okay.
Okay,
And so
so
for you, mathematics is primarily concerned with quantity or numbers and the way that you're defining it right here.
and the reason why I'm not just being combative, right? The reason why I would say halves and quarters and negative numbers and infinite numbers and all these extensions, right, to the number class that we use all the time, I, whatever it happens to be, that those aren't numbers, is not because they're not useful, is not because they're not practical, is not because we can't create them in our minds. It's because they're incompatible with the real thing that we abstracted from the world. So let me say Sherlock Holmes is a fiction, right? But you made Sherlock Holmes on the basis of real things that you abstracted from the world. You know what humans are, you know what it means to deduce, you know what crime is, whatever it happens to be, you put them all together. So are negative numbers and fractions like Sherlock or like a real man?
I mean, so I would just I guess so I see what you're saying with the
Okay,
abstraction of numbers and quantity, and I really like it. I think it's really
okay,
brilliant. But I guess you can abstract other things, like
sure.
direction, you can abstract direction, to the
Yep.
point where it's like, oh, I can imagine this turning this, and this way. And I'm going to abstract that as a vector, maybe an abstract object that's a vector, and just to denote the three directions that this thing points in space. And that would be a different
Uh-huh.
abstraction than the abstraction that you're doing with quantity.
Sure, sure. So
And then,
topology, right?
but it
Is
would
those,
nonetheless be real, I would contend.
oh, there's no doubt. So like the Königsberg Bridge problem, right? So you have what's the minimum number of bridges you have to cross in order to cross them all, and things like that.
yeah,
All those topological questions in my book, I address those, and I say, these may be legitimate extensions to mathematics because there definitely is something here. A Mobius strip is definitely something different. It's something new, right? And it's non-Euclidean. It doesn't seem to be covered by the same general rules that geometric objects are covered by. All right. Um, the only question is, are those extensions math? Oh,
okay,
yeah, there are lots of sciences we can have, right?
okay.
But I'm not sure really it's the study of the quantity, right, in topology that you're really concerned about. It's the same with what they call handedness, right? Right-handedness, left-handedness. And you'd say, well, that's all relative to a face. So unless you're going to definitely include faces in your account, handedness is not math.
I see.
And if
Right.
you include faces, face is a physical thing, and therefore it puts it out of that realm as
So
well.
I guess you would call it different, the different branches of mathematics today, as
Yeah,
as they're called. You would maybe call them specialized sciences,
sure, sure.
right? So like
And
topology would be a science, group theory would be a science.
oh, absolutely,
Okay.
absolutely. As long
So
as there's
interesting. And so
something
why do you think they all get called math? What's your perspective on that?
okay, well, I think, well, first of all, there's no doubt that topology is called math because it has something like geometry in it. In
Okay.
other words, you're talking about surfaces, right,
Hmm.
in topology. Handedness is a little different, rotational direction is a little different, but definitely topology and the whole idea behind a Mobius strip or whatever Königsberg Bridge problem you're solving or something like that it seems that you're dealing with two-dimensionality, right? Like surface. And it seems like that surface is still geometrical, it's still Euclidean, right? So I think that's the case. It may be, however, that what you're bringing into it to make it topology is something that's not quantitative, but another relation. Like you were saying, a vector, it brings in something, but it's not quantity. Direction
Right.
is not quantity.
And so would you say that all these other sciences suffer from the precision problem? Like similarly, like you wouldn't find any topology talk about, I don't know. I really don't know that much about topology.
True
But
north, true north, right?
yeah,
True
okay.
north is a range,
Uh-huh.
right? Okay,
Okay.
yeah.
But
So
I
I think
mean,
yes, they would.
okay, so wow. Okay, so all of our abstractions then and these sciences that we have, I guess, named mathematics would all suffer
Yeah,
from the precision
yeah.
problem then.
Well, remember, I think I solved the precision problem for geometry and arithmetic.
No, yes.
Okay, all right. But then you have what you call the application problem.
Yeah, I guess that's what
So
I mean.
why
Sorry.
is it that the ideals that are in my mind don't perfectly match up with reality?
Yeah.
I have no problem with reality being imperfect. It
Okay.
seems to me
Awesome.
it really is. Yeah,
Yeah.
yeah,
Right. Okay. And
yeah.
there might be ways that we can continuously move forward to get better and better approximations, but it will not
Sure.
necessarily be
Oh,
the
yeah. And finally, I mean, who quibbles about a practical approximation?
right.
Only philosophers.
Yeah, and so another thing I think you'd have a really interesting perspective on, because I was looking at your CV whenever I was writing your introduction, and I saw that you did your undergraduate thesis on the principle of individuation.
Yeah, that's right.
And I really want to know, like, in what sense can you know individual things, like things that are so individual, like, because so there's nothing that is perfectly spherical, but you might again say that it is a sphere, but you can
Mhm.
nonetheless know things about this thing,
Yeah,
that might
yeah,
not be a sphere. Maybe it's a
yeah,
ball, that has
yeah,
certain perturbations on it.
yeah,
So
yeah.
can you maybe talk a little bit about this? Like in what sense can
Okay.
we in have things in our intellect that aren't necessarily intelligible objects in themselves?
Yeah. So I don't think it's possible. Right.
Okay.
All right. So, for example, any description you could give to an individual is conceivable. Any descriptive term you would use for an individual is conceivably applicable to another individual.
Okay.
There is no unique
I
property
see. Because
that
you'll
an
say like
individual
maybe it's
has.
red, it's shaped like a ball. There could be other things that are
collect
red or
collect
shaped like
all of those, as many as
right.
you want.
Yeah.
There's no way to prove that that couldn't apply to another individual.
Mm,
Okay, so even if you were to say, for example, all right, what I'm doing is I'm assuming Euclidean space, and I'm talking about time as a fourth quantitative dimension. So I'm going to say there is no other object which is at this position,
mhm.
three-dimensional position, at this particular time. You say, okay, that might be right, but any object could have been there.
Right.
And it wouldn't have ceased to be the object it is just because it happened to be there at that time. Do you see? So even
Yeah.
if we get down to, you know, precise location in place and time, um, and then of course color and temperature and shape and all those sorts of things are common. Things have them in common. So I
So
don't think. Hmm,
would you say
I
that the
think the
only things that
individual
you
escapes the capacity of the human mind to understand. You need senses for individuals.
okay, and so I guess the only thing that you can have in your intellect about an individual thing are things that are in fact universal
That's
property
right.
that only
That's
apply
right.
to that
That's
specific
right.
thing. And any
That's
knowledge that
exactly
you
right.
would go beyond that would be in your senses. And then
Sure, sure.
and so this is interesting because this would limit our ability to communicate specific things, right? Because anything that we can communicate about actually has to have some sort of universal property, right?
Universal content to it. Sure,
Yeah, okay.
sure.
Wow, that's
Yeah,
fascinating.
words are signs of our thoughts, and thoughts are all universals. There is
Right.
no. You have individual sensations, obviously,
Yeah.
um, but you don't name those.
Yeah, right. That's so fascinating. I'll have to maybe read your undergraduate thesis 'cause
Oh, please don't. It didn't address this question at
Oh,
all.
okay.
I didn't do it very well. So
Do you have any do you know any other people that kind of talk about this idea? This is something I've been interested in, but I haven't
the
I guess
principle of individuation, you're saying?
I guess the principle of individuation, but our ability to in what capacity we know things that are individual.
I'll refer you to Aristotle, right? I think
Yeah. Okay.
best place to begin for that is his
Yeah.
posterior analytics, because it's one of his logical works, and he's
Okay.
talking about demonstration, and he says very, very clearly in there, makes the case, yeah, you cannot know a thing that is not universal.
Right.
Um,
Okay.
yep.
Yeah, I haven't looked at that one yet. That's the one that scares me the most of Aristotle thus far.
Posterior analytics.
Yeah, but
Yeah,
I'll get there eventually. I'll try to get there faster now that you.
yeah.
Um,
Think of it as his epistemology.
okay.
Get a sense
Right.
of it. Yeah.
Um, so I guess just a couple more questions I wanted to ask you.
Sure.
Ones that
Sure.
I saw, especially from the audience, that were interested in your opinions. So what's your opinion on the problem of actual versus potential infinities?
Oh, sure. Yeah. Well, okay. As when it comes to actual infinities, I just ask someone, just show me one, and I'll shut up. I won't say another word, and I
Right.
never ever get one. So, yeah, um, yeah. There are no actual infinities. There
Yeah.
just are no actual infinities. So I go back to Zeno's paradox, if you're familiar with that.
Yeah.
Okay. And I think the solution to Zeno's paradox is not calculus, right? Calculus, where we sum an infinite number and somehow come up with a finite, right?
Hmm.
Um, it's that when we travel from A to B and we go halfway, we don't actually stop.
Right.
Right? So if we were to stop, then of course you could never leave point A and you would never get to point B.
Right.
So the difference between actual and potential is crucial when it comes to infinity.
Right.
Of course, there is an actual infinity, but not in the physical world.
Okay. Yeah, like there exists the concept of infinity.
No, no.
Or
I think our concept of infinity is a negative concept. It's just not finite. No, I think there's a real, actually infinite thing.
oh, okay. I see what you
Yes.
mean.
But we're not aware of it through abstraction, right? We have
Right.
to arrive at it through demonstration and so on.
Right.
So,
Right. Right.
and by the way, Cantor, if you're familiar with Georg Cantor,
Hmm.
um, who he was the one who really pushed hard on actual infinities. His paradigm for actual infinity was God himself. And he says, given
Mm.
that there's God, then there must be infinite numbers. Oh, wow.
Right. Right.
Okay. Mm.
But so you wouldn't have a problem, I guess, with potential infinities. I mean, I would think of a continuum as a potential infinite.
Sure,
Okay.
sure, sure.
Right.
All that means is as many as you want.
Yes. But yeah. Okay.
Yeah.
Um, and another question I wanted to ask you about, which you kind of mentioned in passing, is I guess your position maybe on structural realism of mathematics. I think that you appeal to this a little bit,
Oh,
where you said,
structuralism.
yeah, I mean, well, so you said that, so structural realism, at least the way I understand it, is
Mm-hmm.
this idea that things actually have mathematical structure to them. Like
Yeah,
you would understand, like I can collide two balls with each other,
yeah,
and maybe you can
yeah,
do this Newtonian analytics on them, and you
yeah,
can say like
yeah,
they'll collide and they have these forces and they go this
yeah,
specific way.
yeah,
And you might
yeah,
say there's
yeah.
imperfections, I guess, about the way that we conceive of, the balls whenever we're, trying to do
Wow.
calculations
Wow.
on them.
At what level do you think are there imperfections there? Because I think the physics of it is pretty perfect.
That's what I mean. So, I mean,
Okay.
there could be imperfection like, oh, maybe I modeled this ball as a sphere, right? Which we talked
Okay.
about is
Okay. So
not precise.
shape imperfections. Yeah.
Yeah, so there's shape imperfections, but so yeah, exactly. So what is that's exactly my question is what is your position on the relation between things that happen with their collisions? Even if we can't model their individuating properties perfectly,
I
the
think
F
there
equals MA
hasn't.
of it.
Okay. Maybe I'm misunderstanding your question, but it seems to me it seems to me that as you go from Newton and then to quantum theory, one huge difference is the is indeterminacy. In other words, is chance.
Right.
Okay, so Newton conceived of his laws of motion as absolute, you might
Hmm.
say,
Yeah.
and universal.
Yes.
So, given that's why I said, are you talking about shape imperfections, or are you talking about other terms? Because I don't think I would conceive of the physical world as combined in a physically, that is concerned with physics, imperfect way.
Yeah, so I just meant there's going to be problems, if I have two literal billiard balls that collide with each
Yes,
other, there's going to be
yes,
shape imperfections and like
yes,
modeling just by the nature of it being an individual,
yes,
as we talked about. But
yes.
there's this relation, I guess, that I could say that, their momentum is conserved and I can get these angles, insofar
Right,
as I.
right.
So
But
what about that
that would
structure, I guess?
assume that you know the velocity and play position of each one of the parts.
Right. Okay. But what I
Okay.
mean is, I agree with you that I totally
Okay.
agree with you that that's an
Okay.
issue.
Okay.
But the question is, the momentum equation, momentum equals mass times velocity.
Right.
Do you still think that that is a real structure that happens like that equation has to be true, no matter,
That's what
barring
I'm
that,
saying. I
barring
think
the
once,
epistemic problem that we have, mass and velocity,
yeah.
will that
Well, wait.
equation be,
Okay. So it's not, so you say it's an epistemic problem, but there are physicists who say it's not epistemic, right? It's
yeah, no,
real,
yes,
that there's
right.
real indeterminacy there.
Whichever one you want. I mean, whatever
Okay.
indeterminate.
Well,
Yeah.
if it's the latter, then clearly no, there's the structure itself is subject to indeterminacy. So I would say, what would it mean to study such a thing, right? If it's merely epistemic,
Well, there is a difference. I mean, even if you're talking about quantum mechanics, where there is many people interpret it as having
yeah,
real
yeah,
indeterminacy.
right.
There is still a relation that holds, which is the Schrodinger equation.
Mm-hmm.
And so even if you're maybe hazy on those positions, you could easily talk about the expectation value, or if I were to do this a billion times, what would the most likely point be? And so I
So
guess
you're
are
gonna,
those relations that are those, what is your position on relations like that? Does that make sense?
yes. I mean, I think I'm understanding you. So Newton's laws then become extremely probable,
Or they give the most probable outcome.
right?
And that's my take on it. I think that they give the most probable outcome, but
Of course, but okay. A probable conclusion is not a demonstration. So if I take my lines, the unidimensionality, and I put three of them together, I can prove that the angles are equal to 180 degrees, right?
right.
That's not probable. And that's not an approximation. That's a demonstration. That conclusion is true, right?
Hmm.
If you say Newton's laws provide us with a kind of between macro, and highly micro description of the world, the most likely outcome, I would say, well, you're not doing science in the sense of Aristotelian science there.
Interesting. But I mean,
Newton would have said, yeah, if you know the velocity and
yes.
mass of
Yeah.
every particle there, you can absolutely predict the result.
Yeah, okay. But so there's this issue still where if I say that momentum equals mass times velocity,
Mm-hmm.
even on the quantum mechanics view, the view that I would just, readily subscribe to, that there is in fact some indeterminacy, like fundamental in most things, even though it gets really small at the
Okay. Yeah, yeah,
classical
yeah,
level.
yeah, 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 yeah.
Um, the indeterminacy is really only in one of those variables. So if I have momentum equals mass
Okay.
times velocity, then
Yeah.
determinacy is in velocity. But
Okay.
nonetheless, if I knew the velocity and I knew the mass, I would still know
Yeah.
the momentum, even though there's indeterminacy in the velocity. And so my question,
You're
I guess,
saying real, that's real indeterminacy, meaning I can't measure it, or it's not one thing or another.
oh, okay. Yeah, I guess I see what you
Because
mean.
velocity requires position. It presupposes position. And
So I guess this is getting in the nitty gritty, I guess, of my philosophy
yeah,
of nature. But
okay.
I would say that there are you could distinguish between things having certain potentials and things having certain actualities. I think that we can
Okay.
measure things and would like when we measure things, things can go from potential to actual in that sense.
Oh, wow.
But once it's actualized, like if I know the velocity, and of course there's always going
Okay.
to be some error bar. Like I understand that there's this problem that we were talking about with knowing
Hmm.
individuals. There's always going to be some
Hmm.
error bar. If
Hmm.
I know the velocity and I know
Yeah.
the mass, I would
Yeah.
know the momentum.
Okay.
Does that
Okay.
make sense?
Okay. I'll take your word for it
Okay.
because you're going above my area of
Well, so this is me just asking a question. I'm just saying, barring the indeterminacy of the real world that we have of
okay.
measuring these things, I guess
Okay.
what's your opinion of the structural relations, which is,
Wow.
momentum
Okay.
equals mass times
I'll
velocity?
say the same. I think I'll say the same answer. So you're saying, according to you might contemporary physics, there's a fact of the matter. There's a
Sure.
way it is.
Sure.
Wow. So again, you're falling. If I, in my understandings, then you'd be falling back on the epistemic part. Observation. Observation is a factor. If observation is a factor, it's epistemic. If we weren't looking at it, what would it do?
Yeah, I
Would
mean,
it necessarily do one thing, or are there a number of possibilities that could be actualized?
I would say that there's a number of possibilities that could be
Okay.
actualized, but they
In
need
which case, you
they
can't
need a
predict.
they need an actualization, in order to put it into act, of course.
But is that so fundamental? I understand indeterminacy in natural philosophy now
Yeah, yeah.
to be there are a number of equally possible outcomes, and there is no determining factor that decides among those outcomes.
Yeah, but usually in indeterminacy, there is a thing in which you can determine something which was previously indeterminate, typically by a measurement, is a simple measurement.
Determinate. Okay. So apart from observation, is there anything?
Um, I think that there could be. I mean, so
Okay.
yes, I wouldn't say that a measurement, I would just say there needs to be something that actualizes a potential. It doesn't
Yeah.
necessarily have to be an observation.
Wow. Wow. So do you think there's pure chance?
Mm, yeah, I mean, there are things where you can only talk about how they are potentially before they're actual, which you would describe a science of chance in a way of probability.
Of probability. Hmm. Hmm. But would there have had to have been a cause that made it that way?
Yeah, I
Determine.
mean, there would have to be something that actualizes a potential.
Wow. Okay. All right. All right. All right. All right. So yes, we agree.
Okay.
So I am I believe that every effect has a determinate cause.
Okay.
Yeah. Yeah. In natural in the natural world.
Right.
Right.
I guess one of the big difference, and we don't have to quibble too much about this point, but I would say, I guess I'm more of a realist, I guess, in the idea of potentiality. Heisenberg, whenever he discovered quantum mechanics, he said it seems like the quantum wave function is something akin to the Aristotelian potentia, but it's something that we can actually it it it's it's something that we're kind of measuring or really thinking about or positing that it
Mhm,
exists in
mhm.
reality.
Yeah.
So I guess I would say that there is potentials that can exist like as potentials before they're perfectly actualized.
So pure potentialities without
Yeah,
being actualized.
right. So I guess I would describe it in there's things where it's like you move beyond prime matter, right? But just because you went from prime matter to the next step doesn't mean that everything about a substance is actualized, like all of its accidents are then actualized or things like that.
So the potentially existing is a real kind of existing.
Yes. Yeah.
Okay. And is that different from the purely potential?
So, I mean, if it were purely potential, then you wouldn't actually be able to put any bounds on it, right? With wave functions, with like quantum wave functions, we can say it's either spin up or spin down. If it were pure
Mm-hmm.
potential, I wouldn't be able to say anything about it. I'd be able to say it could be anything at all, you know.
Could it be nothing?
Um, I mean, I guess that's kind of what prime matter is it's in a
Mhm.
sense it's so variable that it is in fact
It's
nothing.
a nothing that can do.
Yeah, right.
Yeah.
Yeah, right.
Yeah. Yeah. So getting back to structuralism, then I mean, um, yeah, in a way that's not. I wouldn't say there's so much that's being brought in here that to my mind is non-mathematical.
Okay.
But I almost feel like, okay, I've been We're now discussing
I'm
natural
sorry. Yes, I'm
philosophy.
still getting used to your view of math, so maybe I
Yes,
still
yeah,
accidentally mixed
but
it.
I have a view about natural philosophy, right? So
Right.
it's not a place that I'm uncomfortable going.
Okay.
It's just I haven't really thought, where do I stand? I do believe that every effect has a determinate cost. So, in other words, there's no such thing as an indeterminate cost.
Okay.
Um, Now, on the other hand, I do hold that not all effects are determinate effects. So,
Okay.
yeah, that's really what I can say.
Okay.
Now, could there be a science of that? Yeah, I think that is natural philosophy or physics,
Yeah.
especially if you're talking about describing them.
Okay.
Mm-hmm.
Yeah, yeah. I guess, yeah, I had that question written down, to ask you about the mathematical structuralism, but I guess the idea of mathematical structuralism by your definition of math is not actually math. So, okay, I see
Yeah.
what you mean. Right. Okay.
Yes. Yes. Yes.
All right. Well, I don't think I really have any more questions
Okay.
for you. That's what I had thus far. And
That's
yeah,
fine.
if you don't have anything, if you have anything else you want to say, you can go ahead and say it. Or
Uh, well, yeah, I think what I've encountered among mathematicians, among my colleagues and other students, um, I'd like to see a return to whatever, however you define math, at least regarding that part of math which investigates the properties of quantity, right? Arithmetic, geometry, and the extended mathematical sciences for its own sake. I'd like to see people give that a little more respect.
mm,
Okay. So, especially it's odd in the United States, we're so practically minded, right? That I've sometimes gone to mathematicians and say, what about these wonderful things? What about the asymptote of Apollonius, or what about the Pythagorean theorem, or what about the square root of two? And I walk away from those things in awe, right? It's a little bit like the way people treat pi today, in awe, right? And I'm like, there's something here that is the way it is, independently of anything we've ever done. It's waiting there to be discovered. Um, and I sure would like to see more people at least say, well, that's a worthwhile activity. Do you see
right.
what I'm saying?
Right.
Pure
Instead of
math,
going into these maths like set theory or group theory, maybe go back to the math of what you talk about.
perhaps,
This-
although I have no difficulties with the marvels in set or group theory.
right,
What
right.
I'm saying is, if you're doing set theory or group theory only because you have some kind of problem to solve,
I see.
right, as opposed to investigating the thing for the wonderful conclusions you can learn,
Hmm.
right? So there's a story that's once told. Euclid was approached by a student who was complaining because he didn't want to learn geometry because he saw that it had no practical benefit. And Euclid said, give the man a coin because he has to earn something from what he learns. All right. And I have the same attitude, right? So the sorts of questions we've been talking about this whole period, I mean, they may have a practical benefit, right? But I think they're worthwhile pondering and discussing for their own sake, right? It's a very human thing that we've done here. And so that's what I'd like to leave with people is I think the philosophy of mathematics has led me to see much more clearly how marvelous it is to think about numbers, right? To just wonder what there is that we can know and what there is that we haven't yet discovered. So that's what I'd want to say.
Right.
Yeah.
I couldn't agree with you more. I think
Okay.
there's definitely a need to ponder things that maybe don't necessarily have practical application, and
Yeah.
that's a very truly human thing to do.
Yeah.
Okay.
Okay.
Well, thank you so much. And
Well, you're very welcome. Thanks.